Cool. Moving on to amplifiers and interference. Why do I need to know about this? I asked myself this many times when reading about electricity. But it is kind of important because we want to know what the ideal properties of an operational amplifier are. And this is because we want to know when an electromedical signal is being faithful to what truly is happening in the patient's physiological reading. Also, obviously, currents or signals start off as an analog signal and they need to be converted to a digital signal, and this allows them to do that as well. And the sampling rate of the analog signal must be appropriate, otherwise we'll get something that doesn't really represent what's true in real life. So this is a diagram of an operational amp, and essentially, like the name, they're designed to amplify. So we talk about the gain of an amp, which is essentially how much the electrical signal is increased. They have the feature of having a very high input resistance, and this avoids drawing current from upstream. And another way of saying that is that it has a high common mode rejection ratio. And therefore, it's another way of neutralizing upstream circuit noise as well. So this is a differential amp. So as you can see, it has two inputs. One is a non-inverting input, so the sign will remain the same. And then the other one is an inverting input, which inverts the input signal sign. And again, that is a way of neutralizing any upstream noise. Because if it's common to both, it would be neutralized. So we can combine these with other elements, and then that also allows you to feed the output back into the inputs. And you can then use it within the other functions, so differential, integrator, inverting functions as well. So just to put, again, it back into a context of an ECG, this is a typical sort of the processing of the signal to finally appear on our computer at the end. So the ECG signal is first amplified by the differential amplifier. You may also have other signals that are coming through via a Wheatstone bridge, which also allows you to filter out the noise, as we said before. And then it will go through the CR, RC filters, which allow only a certain range of frequencies to be amplified. So for an ECG, it would be 0 to 100 Hertz, for example. And then there is an analog to digital converter, which basically, you don't need to know too much detail about that, but allows you to visualize it on a screen. So for example, the smooth waveform here would be the analog signal, and we take a sample from each of these points, and it essentially recreates that on a screen. And you can imagine if you didn't sample it often enough, you would get, like, for example, we did there, then there, then there, and it would look like a very different waveform to what you actually have. Cool. Quick knowledge check. So true or false to the following statements regarding why op amps have a high input impedance. So is it to reduce the input voltage, true or false? Just shout out. Again. So it basically, well, we'll comment into it. So is it to reduce signal distortion? Yes. No! What? Wait. Okay, no, I think that's incorrect because it reduces the current drawn in by the amplifier so that you don't degrade it, but it doesn't actually affect the signal itself. It's a very confusingly worded answer, that one. So this one is correct because it reduces the current drawn in by the amplifier. D is incorrect and E is correct because it does not degrade the signal, but it doesn't really take anything away from it either. And then that's also incorrect. Well, I can't remember which one is. You could do that anyway. Oops. So, and that's just one more, I think it is, another true or false regarding the purpose of a differential input of an op amp. So this is the one where I was talking about it having two inputs, an inverting and non-inverting. So Is it to mathematically differentiate the input signal? No. Is it to invert the sign of one of the input signals? So I guess I'm going to sleep. That is correct. So you know it has an inverting and non-inverting one.
Yeah.
So one of the inputs will be inverted, and that basically gets rid of noise. To double the magnitude of the input signal, that is incorrect. To change the sign of the input signal, that is incorrect. I don't really know why, but it's to invert the sign of one of the input signals, not to change both. And then to cancel the effect of unwanted input signals, that is correct. So that's how it sort of, if it changes the sign for one of them and it's common to both pathways, then it will get cancelled out. It's quite similar to the Wheatstone bridge idea, which is why it's very confusing. We've all heard of the Wheatstone bridge. This is a stone bridge also. This is a Wheatstone bridge. So what is a Wheatstone bridge, or what is the purpose of a Wheatstone bridge? Essentially, it is to reject noise signals. So an example of this would be in an arterial line, where obviously movement of the line and movement of the patient might produce noise. We obviously want that to be cancelled out. We only want to see the small, minute sensation on the screen. And it allows it to be detected and amplified, basically. So it's similar to what we were talking about before. So it is a type of voltage divider, but the structure of this circuit is basically a bridge circuit where the voltage dividers are connected back to back. And this means the bridge is balanced because there's no potential difference between these 2 points, X and Y. And therefore, no current would flow between them if they were connected. But with the Wheatstone bridge, we put a transducer on one of these sections, which basically means that only the signal that's going through the transducer will cause a potential difference in the voltmeter. And any other high voltage signals which go down both arms, they'll be cancelled out. And so that's how it basically gets rid of noise. So an example of this transducer would be like the strain gauge diaphragm in an arterial transducer. You can also add another transducer to the other side if you wanted to make it even more sensitive. So key points. So this kind of looks kind of familiar, doesn't it? When you look at the arterial clip that you put by the side of the patient at the level of the heart. And that basically contains the Wheatstone bridge. And it's a pair of potential dividers connected in parallel. It is a means of detecting any small potential difference between its parallel arms, and therefore any unwanted signals are eliminated. How are we going to sort of relate this to the patient, and which kind of tissues can be measured in terms of excitable tissues? So can anyone give me any examples of a biological potential or tissues in which an electrical impulse can be transmitted? Yeah. So heart, cardiac tissue, by ECG, brain signals, EEG, and the final one is muscle tissue, EMG. So when we look at analyzing these kind of biological potentials, they're again composed of sine waves, but they're in different frequencies. And the analysis that we use to sort of compose all of these different frequencies into a single one is the Fourier analysis. But the size of the measured potential does depend on a couple of things. So we know that when the heart is bigger, the size of the potential is larger. And so that's the excitable tissue mass. And also the amount of tissue separated from the heart from the electrode, which we know from obese patients with COPD. That will also dampen the signal. This is the EEG, which we have obviously seen on our BIS monitors. The EEG will measure the summed electricity in the brain, and depending on the area and the state of the patient, so are they asleep or wide awake, there will be a predominant frequency. So, the gamma frequencies, high frequency problem solving concentration is what it's related to. Whereas when we have some of the general anesthetic they will generally have delta waves being predominant, and that's a sleep dreaming state. And then there's the EMG. So skeletal muscle tissue does repolarize very quickly, and the activity is dependent on the number of motor units stimulated. So this frequency is a lot higher than that in cardiac muscle because of the short repolarization. As I mentioned before, defibrillators are a type of clever capacitor. So they collect and they discharge the electrical charge. And essentially they have features that make this more efficient, more safe, including the gel pads, which basically minimize the impedance when you apply the pedals, although we don't know if no pedals anymore. That's very, very dated, but we still obviously apply pads which have jelly on them, and that will minimize the impedance. Final example is nerve stimulators. So we've got a peripheral nerve stimulator here, which we typically put on the ulnar nerve, and that will transmit obviously the signal through the skin using gel electrodes. And then next to that we have a needle nerve stimulator. So this is the one that we might use for nerve blocks, and it's useful because we can measure how much voltage we need to stimulate the muscle. If it's incredibly low, then that probably means you're in the nerve itself, so you should not inject at that point. But essentially, you should need less and less of a voltage to actually get the neuromuscular junction to cause a contraction.